All right, I think that's my cue. Welcome. Have a seat if you don't already. I'm Mads Torgersen from Microsoft. I'm the program manager for the C# programming language. I'm the guy who gets to enjoy writing the language specification and run the language design process. So I was one of the people involved in putting the async feature into C# and VB in the first place. Oh, thank you. Wow. Okay, we're done. Bye. So I guess we have some fans of that feature in the audience. That's good. So let me start out by a show of hands, even though I can't actually see much from up here. How many people have used the async feature in some way, shape, or form? Okay, that's good. That's the majority of the audience. How many have not? A few. Okay. Okay, we probably don't need much of a primer. I apologize a little if you haven't looked at it. And how many are other? Oh, okay, everybody has either used it or not used it. That's good. So this talk is going to focus on various. It's called async best practices. It's going to focus on various problems or situations that we kind of realized after we put the feature in and started having people use it, that okay, there's some things here that are really hard or that people struggle with, and we tried to take some of the most common ones and boil out the best guidance for dealing with those. And that's what this talk is primarily about. So the 4 points that I want to make sure that we get through in this talk are here. I'm going to say them up front. You're going to probably forget all about them, but we'll visit these along the way. And if we have time, we can touch on a few more, but we may not have time. So first of all, async on void returning methods is really dangerous. You might ask, why did you put it in? Well, it's also really necessary. But it's one of those things that we want to warn you of as a common smell, and we're going to look at some of the examples of why it's a bad idea, how to work around it when you have situations involving it. So that's one thing. The other one, the next point we want to make is about essentially the difference between CPU-bound code that's heavy work and wanting to run that in parallel versus IO-bound code that is essentially work that takes a long time, but it's not happening on your machine, but somewhere else out there, like downloads and stuff like that, and how that should impact your code. We'll look a little about how you can use async to clean up messes around event-based programming that can get very hairy sometimes. So there's some tips and tricks there. And finally, an important thing that we'll look at is when you write libraries, you should make sure that they don't essentially lie about what they're about. If they're not really async, don't make them look async. If they're not really synchronous, don't try to make them look synchronous, if you can avoid it. So let's start right out. We had a user. I'm gonna actually read from an email that we got from a user around this kind of problem. I have a Silverlight page that uses RIA services async to download the data for the page, and this works fine. If the user waits for a few seconds before they click on the print button. But if they click the print button right away, before the data is loaded, then somehow the print doesn't have all the data. What's going on? Maybe you recognize this kind of thing. Okay, apparently something wasn't ready when I clicked. So this kind of code here. And when we looked at the code, it turned out that they were using async void in places where they shouldn't. I'm not actually going to share the code from this user because it's a little involved, but we're going to, let's make the point really clear here. You should not use async void unless you absolutely cannot avoid it. Anyway, so I'm going to use a different example here that that's simpler but highlights the issue of using async void. So it's very common looking code here. I have an event, a button click event. It's calling an async void method. The event itself is async void. It's calling an async void method to try to send some data. And it gets a response back, and it assigns it into a variable. And then after the button click has called the send data method, it waits for a little while. Then it to make sure, hopefully the data got, the thing got through. We kind of put a delay in to make sure that the interaction happened. And then hopefully the variable filled up, and we can print things out. Now, of course, if you look at how this executes, when the event handler is called, control comes in, we call send data. It goes to the send data method, starts executing it. Now, as soon as it comes to the first await, you guys know what happens? Yes, you do, but you're not going to tell me because he's doing the talking. I'm sure they pay him money to do talks. Why should I? So what happens when you reach an await is that your method returns. What it does is it signs up a callback on the thing you're awaiting to say, resume me later, and then it returns. So the method returns back out for resumption later. Well, the next thing I'm doing up here in my event handler is I'm also awaiting something. So now I also return to my caller, whichever thing fired the event in the first place, and I'm out. Sometime later, so now I'm awaiting in two different places. Sometime later, one of these will resume, and then sometime later again, the other one will resume. But we don't know which order they'll do it in. Maybe most of the time, the await and send data will fire first, because typically it won't take 2 seconds to request something. But maybe one day it does because the network is slow, and you see these strange, apparently non-deterministic failures happen where it didn't get everything before it needed to. So that's one way that you see it. Let's look at another variant here where we're not even waiting for the result to come back. Another issue that happens here: we come in, so same as before, we get into send data, we await the request. Now something else happens. The thing that we're trying to, the get response async method that we're trying to call here, it actually completes with an exception. Something went wrong, okay? So when something goes wrong in an async method, then the task that the async method returns still completes. But when you await it, you get the exception out instead of a result. So what happens here is that the await throws an exception. But the exception happens after the method has returned. So we await, we return to our send data method, return out, and then once the task is complete, the event throws an exception. However, the exception doesn't come back to our original caller, and it doesn't get caught by the catch handler because we're already out, right? No one was there to hear when things went wrong and to deal with it. What happens instead when you have an async void method that throws an exception, because it has no task to put the exception in and say pass it on or whatever. What happens instead is it looks at where it's running and it takes that thing down. All right? So this send data method here, it's running on the UI thread. It goes to the UI thread and says, I have an exception. I don't know who called me. He's gone long ago. I don't know what to do with this exception. The UI thread says, fine, let me kill the program. You got to crash. Okay? Even though you have a nice try catch up in your event handler there, you are not awaiting the exception, so you're not catching it. Okay, so these are two flavors of this thing going wrong. So the principles that are worth keeping in mind here is that async void is really a fire and forget mechanism. That's what you saw. You kick it off, and there's no way that you can know what happens next, because you're only getting void back. You're getting nothing back to talk to say, what happened? Did it go all right? What was your result? It's fire and forget. And fire and forget is almost never what you want. You can't know if it finished. You can't know if it threw exceptions. So what you should do is only use async void when you absolutely have to, when you're top level. And that's typically in an event handler. It can also be things that aren't really event handlers, but are used the same way. So async void virtual methods, we'll see an example of that shortly. It's a way that people have event-like stuff. You really, really, really have to return tasks whenever you can. Except when somebody's shoving a signature down your throat saying, this method has to return void. Otherwise, you're not fitting the event handler signature, or you're not overriding a method of the right signature. Even if you want fire and forget functionality, still return a task. It's up to the caller whether they want to use the task for anything or not. They can always choose to ignore it. They can be very explicit about ignoring it. But you should not do async void, because then no one has a chance of knowing what happened. I think I said it strongly enough, didn't I? Yeah, there's a lot of nodding. This was a very sort of do not like thing. We have some more creative, some more sort of positive ones down the line. Okay, there are a few things that are gotchas here. One is that, as I said, it's not always. First of all, let's look at how to fix the code from before. Sorry. So, of course, what you should do is take your send data method, make it async by calling it send data async, by returning task from it. Then when you call it, you should await it, and everything works out fine. Right? So this is easy to fix. It's just keeping that discipline. But sometimes this thing is sort of a little more hidden. Let's take a place where it's a little more hidden. Here we have a couple of event-like methods. They're not really events, they're not signed up with delegates, but they're virtual methods returning void that are sort of called when certain things happen. These are virtual methods from the Windows runtime that you will run into if you're writing a UI-based app like writing a store app. There's an unnavigated to. Clearly, this is sort of event-like. And it returns void because events do that. And it's also virtual, so you can override what happens when you navigate to this page. Pages also have a load state that's similar. It's also an event. That's fine. These are event-like, so async void is probably good. Now, the first thing this particular override does is to call base. And here's the thing that has puzzled a lot of people, like, I'm following your advice. I'm using async void only on the top level, but something still goes wrong here. We've heard a lot of customers complain about these particular two methods. And the thing that goes wrong is that when you call base, the base implementation of one of the event-like things actually calls the other one. So the unnavigated to calls load state. This is essentially an async void method calling another async void method once you override them, right? So here it goes wrong. But here, the problem is a little worse because you don't really have an option of returning a task like I just told you to. You can't return a task because you're overriding a method that's void. So what should you do is essentially the question. Let's look at how it executes here just to see the problem in action. I call base. It calls load state. I get to the await. I return. I get to the await. I return. I'm out. Now, which of the awaits continues first is again a race condition. Whether in this case, I'm setting up an image source, whether that happens before I use it, it all depends on the race. So I introduced a race condition inadvertently here. So the medicine here really is to say, okay, I can't return a task, but maybe I can still get a task from the callee to the caller by other means. Okay, so still use tasks to communicate completion. The way you do that is you take the async bit of the load state method, the thing that loads the bitmap in this case, you factor it out into an async method, an async helper method. Now that one will return a task. You call it from load state, and instead of awaiting it, you stick that task in a variable that's shared with the caller, with the unnavigated to. Okay. So when you get called, nothing async has happened yet. You have a task in your hand. You share that out before any awaits have happened, before anything has returned out. And then when the I don't have an arrow diagram for this one. Then when the unnavigated to gets to the place where it needs the bitmap, it knows that there's a task for it sitting in a variable. It can await that task and make sure the bitmap is there before it gets it. Okay? So use tasks to communicate completion, even when you can't do it through the return value. Factor it out, take the task, and pass it on some other way. Tasks are always the best means for communicating about completion. Okay? Good? One more thing on this topic. and then we'll be done with that. You can't always see when you're doing async void. We have async lambdas in the language. Now, a lambda expression does not declare its return type. So you can't look at a lambda and see whether it's void or not. It so happens that async lambdas that don't return anything in their body, they convert just fine to delegate types that have void return, and they convert fine to delegate types that have a task return. Both are valid conversions of a lambda to a delegate. Okay? So that means that depending on what delegate type happens to be expecting the lambda, I either have async void or not. That's very subtle, right? So this is one of the very subtle issues that came up that we didn't really kind of anticipate when we designed the language. Maybe we should have done something, but it was too late. So now you have to live with this. Yeah, that's the lesson. You have to live with this. Now, there are ways to deal with it. So luckily, or maybe because we had a bit of foresight, a lot of methods that expect lambdas actually have overloads that deal with the fact that lambdas can be async. So if you look at the overloads of task.run, there are two, actually more overloads. There's one that takes an action, and there's one that takes a func of task. And the way it decides when you call it like we do on top here, the way it decides which one, the rules are designed so that it will always pick the task returning one. So that's good, right? So if there is an overload of the method you're passing the lambda to that expects a task returning delegate, then that's the one we'll pick. The language does the right thing for you. Good. Task.run, no problem. All is good. Async void's not going to happen there. The problem is, oh, by the way, aside, we had Visual Basic in the title. I'm going to show most things, but not all things in C#. Visual Basic does not have this problem because in Visual Basic, lambdas that are void returning have a different syntax from lambdas that are task returning. One is async sub and one is async function. So this is a C# only problem. Here's a situation where there's a method that does not have an overload for a task returning delegate. So the dispatcher's run async method, despite it being async, it's actually not prepared for taking async lambdas. It's only prepared for taking synchronous work and dispatching it, that chunk of work. So what happens here if we call it with an async lambda? You can see the signature down at the bottom here. It expects a dispatched handler, and the dispatched handler is void returning. What happens when we call it with an async lambda? Well, it starts running the async lambda. It gets to the await. The async lambda returns. It says, oh, the job was finished. Let me complete the task that I returned to my caller. So it kind of claims that the work is done, even though there was more work in the lambda to do. Because the lambda was async void, the method can't know that the work isn't done. Okay. So again, the trick is the same as before. Find another way to communicate completion between, in this case, the lambda and the caller of dispatch.runAsync. Okay, use a task or something like that to communicate the actual completion. All right? Good. Here it actually shows you here how it just runs out, gets done, and then this work will happen sometime later. You won't know about the completion of it. You won't know about the exception that happened, stuff like that. Factor it out into an async method that returns a task, stick that task somewhere, pick the task up and use it instead of just relying on async void. This is really hard to discover. And so typically, because there's no place here where you see async void in the source code, so look for async lambdas. You can search for async lambdas more easily. Async open paren, that should do it, right? And look at whether they are in places where this could likely go wrong, especially if you're starting to experience these telltale effects, these smells of, whoops, sometimes it doesn't do what I thought it would, and sometimes it does. Okay? Look for async lambdas. Okay? When you see an async lambda, check it out. That was sort of the last piece of guidance here. So that's all I want to say about async void. That is the most important lesson here. It's one of those features that we thought about for months when we designed the language. We were like, should we have async void? Should we not have async void? We know it's going to be dangerous, but we also don't know how to write top-level events that are async if we don't have async void in the language. If you can't write top-level events, it's a pretty poor feature because that's like 90% of what people do with it. So there, it's in there, it's a little dangerous. We try to help you sometimes with diagnostics, but we can't catch it in every case. Okay? I shall not talk more about async void for the rest of this talk. You can breathe more lightly now. Now we're going to look at another scenario. Here's someone who is looking at a complaint about code being slow. They have an ASP.NET Web Forms page. They load some data, and let's actually show a picture of their app here. It's kind of a sketch. They're in real estate. They load some data about houses, and they show them. And they're loading each house sequentially, so it takes a long time, and users complain, it takes forever to get these 20-some houses up on the screen. So this guy's like, I want to parallelize. I spend almost all my time in my serialization code. I want to parallelize the serialization, or deserialization rather, of all this housing data. So I should probably use the thread pool, right? I should use the task parallel library and do parallel.for or something like that. So I'm deserializing all the houses at the same time. Then it'll go much faster. So that's good thinking. And you can certainly see, like, if you think about the sequential deserialization of the houses here, if it takes 100 milliseconds per house, which is sort of around what it did, and you do it all in a sequence, well, you're going to have half a second, 500 milliseconds. You do them sequentially, one at a time, 500 milliseconds before you're done. Okay, so we can definitely improve on that. Let's try to make it parallel. We use parallel.for, which is essentially a library for loop that tries to run things in parallel. What it'll do is it'll use the thread pool and put these on in as parallel a fashion as it can. This is more precisely what it does. Let's say the machine has 2 cores. It'll have a thread per core, and it will schedule the work onto these cores as they become available. There's no point, if you're doing hard work and maximizing out the usage of your cores, there's no point in having more worker threads than you have cores. As long as you can keep them busy, this is the most efficient way to do it. And now we're down to 300 milliseconds because we split them on 2 cores. That's better. But let's think about this. 100 milliseconds to deserialize some data? That doesn't really sound realistic, does it? When you go and look at the deserialization method that they have, it's not deserializing for very much of that time. What it's doing is it's doing a database request. So it spends a tiny amount of time going to the database and asking for data. Then it sits around waiting for the data for 99 milliseconds or something like that. The data comes back, and then it deserializes it. No problem. So it's actually not doing hard work on the CPU. It's not CPU bound at all. It's IO bound. The deserialize method spends 99% of its time doing absolutely nothing, hogging a thread all to itself and making it do absolutely nothing. Okay? That does sound like a smell. And that's because of this difference between CPU bound and IO bound. It's super important when you do parallel and async work that you think about which is which. We'll return to this also in one of the other points. CPU bound, you want to parallelize that. You're actually using your CPU. You want to maximize your use of cores and do parallelization on that. Using threads or the thread pool, something like that. If you're IO bound, that may not be the right thing to do, and let's see why. So what it actually looks like is something like this. What they were actually doing sequentially is start something, wait for 99 milliseconds, get it back, deserialize it. Start the next one, wait for 99 milliseconds, deserialize it. Sequentially, 500 milliseconds. What happens when they run it on the thread pool is they start out like before. They start out putting these things on thread 1 and thread 2, but then as these pieces of work sit idle on the thread pool is kind of smart. It sort of realizes, hey, my cores aren't really spinning. So let's put some more work on them by starting up some more threads and taking more stuff in from the queue. Maybe we can get better utilization. So it'll start another thread, it'll wait a little longer. Still not seeing a whole lot of work there. Let's try to do another one. It's got a hill climbing algorithm that gradually spins up threads. And then maybe the last one, it'll put it on the first thread because by now, the first 100 milliseconds have passed. So you end up at 200 milliseconds. It's better, but now we spend a lot of threads, essentially doing nothing. We spun up even more threads and still not getting to the ideal thing. This is the ideal thing, right? You want to do, when the request comes in, you want to start everything right away. Then you want some time to pass, and then you want to deal with the results as they come in. So you start things completely in parallel. No threads involved. You just do those little bits of work to get it started up. They're so tiny, you can do those in sequence. And then you just want to wait around asynchronously and deal with the results as they come in. And when they're all done, you're done, and you only took about 100 milliseconds. So how can you code that up? How can you do parallelization of I/O-bound code? It's actually super simple. This is the code to do it. You get yourself a list of tasks. You go through, it's empty. Then you go through the houses and kick off loading each one of them, each of the 5 houses here. So you go super quick because you're calling async methods, but you're not awaiting them. You just kick them off. You gather the tasks in the list. Now you have 5 tasks representing work that's going on the wire, talking to a database somewhere. But you haven't started any threads. You haven't done anything really in parallel in sort of a machine CPU-based sense. You just kicked off a bunch of stuff, gathered up the handles to reconnect with it later. And then, when you kick them all off, you call the method called task.whenAll. Well, what does task.whenAll do? It takes a bunch of tasks and returns another task that reports complete when all of the ones you passed in are complete. Okay? Then you await that. That means when you have waited task.whenAll of the tasks you started, then that means they're all done. 100 milliseconds have passed or something like that. Then you just grab those houses and you return them, and you're done. Async method. Super simple. No thread pool, no nothing. So one of the problem I kind of showed here was the thread pool kind of being slow in the uptake and kind of takes a while before it gets up to speed. Another problem with using a lot of threads is if you're on a server, for instance, threads can actually easily become the bottleneck. So you really don't want to waste threads doing nothing. You don't want to have those 99% of the time staring down a pipe waiting for something to come. That's not what a thread should be doing. It should be working for its upkeep, right? Keep them exercised. It's good for them. And so, on a server, the number of threads that you're spinning off can become a bottleneck. You really want to avoid that. Save your threads for CPU-bound work. Sometimes, when you remove that bottleneck, you get another bottleneck. Let's assume that you had 500 houses here instead of 5. Maybe you can't have that many requests out in parallel. You're going to clog up some other resource. You just can't have that many requests going on at the same time. So you want to throttle the speed at which you send out your requests. There are a number of patterns for this. There are libraries that are pretty advanced. There's a data flow library that you can get from NuGet that helps you do this. But actually, there's simple ways of doing it too. There's a super simple pattern, which is you come up with, you essentially take the pattern from parallel programming that is worker thread, and you use work or async methods instead. So what I'm doing here is I'm kicking off an async method. I put all my work in a queue. I kick off an asynchronous method that'll work through the queue one by one, asynchronously. So it'll just await, it'll take something off the queue, it'll do that request, and then it'll come back around. Then I kick off a couple more that do the same, and they'll schedule work onto the same thread. They take turns, and when there's a little bit of work, that'll come onto the thread. When there's another little bit of work, that'll come onto the thread. So there are no parallel threads here, but it's kind of similar to a worker thread paradigm in that you have 3, in this case 3, you have n sequential flows that each run independently, so to speak, just doing the next thing. And that way you make sure that there are only n requests outstanding at the same time. Simply, whenever one is done with a request, it kicks off a new one until the queue is empty. Okay. Super simple. It's really not complicated to do these things. It's just recognizing, knowing the patterns and recognizing when should I apply them. Okay? So to summarize about the thread pool here, it's not really about the thread pool. It's about avoiding the thread pool whenever you can. CPU-bound work, use the thread pool to your heart's content. Make sure that you parallelize the heck out of it. Make all your cores spin. It's all good. But whenever you have I/O-bound work, you don't want to waste threads doing nothing. You never want your threads to stare down a pipe doing nothing. Okay? Here's another thing where it's not really async that's causing a problem here. Async is just like before, just the one we saw. Async is providing a solution to another problem. So this one here, we have a user that essentially has event-based UI. They're doing some UI thing, and their code ends up just looking like spaghetti. It ends up being very, very complicated. Here's one example. One example is the app we saw before. It had the same problem. Another example is a game that somebody wrote. It's a fun little game that is for kids. I actually have it running here. So let me log in and run it for you so you can see what it does. And we can talk about what the problems are with it. This is not the game. This is the game. Let's see. So I have it's got sound effects. I have a tree with some apples. I'm supposed to capture all these apples with my finger and put them in the shopping basket here. Because that's, when you shop, you go to a tree and shop apples. It's a counting game, really. You're supposed to count out, okay, how many was that? 4, 5, 6, right? And if I miss it, it just keeps sitting there. There's no way you can lose this game. It's for young kids. And me, apparently. I'm enjoying this. So, simple gameplay. Super easy to explain. First it does this, and it does this. Play again? Maybe not. So, it should be relatively easy to implement this game, right? This is what the VB code behind the game, essentially, what it looked like initially, when they kind of came to us and said, man, this is getting out of hand. I don't know how to structure this. They have event handlers that sign up event handlers, that sign up event handlers, that sign up event handlers, all the way down, I don't know how many levels, right? Because first you run the animation, and then you sign up event handler for when that's done, then do this next thing. And when that's done, do this next thing. And when that's done, and that all becomes nested event handlers. So the reason why they sign them up in nested lambdas is because they want to try to keep their local variables scoped. They don't want to hoist them out as fields and have some kind of global object where things can spill out and things can go wrong. So they try to do the right thing, and they end up running out of horizontal space on their screen pretty fast. And it's impossible to follow the flow of the code, exception handling, all those things. So this feels kind of familiar. They're not doing anything async here, really. But this feeling of callback hell is sort of similar to the motivation for introducing async to the language. So, Lucian, my teammate, sat down with these guys and tried to do a different thing. Let's try to map out a state machine for this. Let's try to do it as a top-level state machine instead. So you start out waiting, then when the animation of introducing it is done, then when people press, then you go into dragging mode, and if the apple hits the basket, then you go to this next mode, and then you come all the way around. And you get this, you describe it as in a state diagram here. Again, it becomes insanely complicated, but in a new way, right? So before things were sort of too local or too nested, and now everything's global events calling each other, and and you have to share all the state between all these different states in the state machine. And this is just impossible to understand. So something is wrong here. We've got to find a middle way, and we can use async for that. Events are not going away, but we can use async to tame them in situations like that. This is really what we would like our description of the game to look like. This makes more sense, right? You have a few sequential descriptions of flow that happens. When you start, this happens. When you resume, this happens. When you press an apple, you drag until it's released, then blah, blah, blah. It's sequential. Okay, maybe there's an if where you go back and until the apple hits the basket, blah, 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 but it's sequential. How can we get to that, and how can async help us do that? This is sort of a tips and tricks kind of thing for event-based programming. Well, we would like our code to look something like this, or the equivalent in C#. Flat flow, first I do one thing, then when I'm clicked, first I wait for the apple to be dragged. Then, if it wasn't in the basket, I'm done. I wait for the, return out. So I use a wait. Somehow, I turned the button or the dragging, let go of the thing event into an async thing, and I wait it. I keep going. Now I do two tasks in parallel. I do the storyboard, the animation, and I do the sound, and I kick those off as async tasks. Grab the tasks. And then I wait for them both to be complete with async that went all, or with tasks that went all, just like you saw in the previous example. Again, nice sequential flow. I do a little parallelization, then I come back in, and it meets, and it's all neat. Just keeps going like that. The question is, how can we turn those events into the async things that I'm awaiting here? How can we implement those helper methods that I'm calling here? That's the trick that I want to show you. And hopefully that can help clean up a lot of it, especially some of that UI code where you're really going through states in a rather sequential fashion, in a way that you could imagine programming with normal control flow. Here's an example. Here's the play async of the animation. It's an async method. It returns a task for when it's done. It takes a storyboard. Actually, let's look at it in C#, because I think more of you are C# guys. So the trick here is to use a thing called a task completion source. How many people have never heard of task completion source? That's a lot of you. Task completion source is a bread and butter thing that we use internally a lot. That's a thing you use to create tasks with. Okay? When you have a task completion source, it's sort of the control panel for a given task. You create one of these, it has a task. You hand out the task to other guys, so they can await that. But you are the one who controls when that task completes and how it completes, with an exception, with which value it completes. You control that on the task completion source. So that's what this object is. This is the puppeteer object for the task, right? So I create one of these guys because I am going to make my own task now. I'm going to not let async make it for me. Now I create the event handler, Lambda. All it does is to tell that task completion source, the event gets called when I'm done. So what the event handler should do is tell that task completion source that the task is done. That's all it does. Now I created that event handler. I go into the setup part of my method here. I add the event handler to the event. I begin the storyboard. Boom. Now the event will fire at some point, but not right now. Then I take the task that I just created, which is now going to complete when the event fires, and I await it. That means I sit here asynchronously, nicely suspended, until the animation is done. Then I can clean up after myself, unsubscribe from the event, and I'm done. The task that because I'm an async method, the task that I return, it's not the task that I created with the task completion source, but the task signifying that this whole thing is done, including the cleanup. That's it. That's all I need to do in order to turn the event into an async thing. Isn't that nice? I'm not sure you got it. Let's look at Let's look at the walkthrough here. I go through until storyboard begin. I await the completion of the task that I set up to complete when the event fires. The event fires. I come back in. I complete the task. So the await continues. So I go through the finally. I complete my own task. And whoever's awaiting me, the main program in this case, now knows that it's time to move on. It's very simple. But you kind of need to know the trick. The task completion source is super for creating your own tasks. The async feature is great for when you have other async methods and you just want to compose the calling of it. You want to create there are tons of async methods in the libraries, right? And if you just want to create some more complex async thing out of those, the async feature rather is great for that. You just do those calls, you await them, task when all, if you have things running in parallel, blah, blah, blah. That's great. But when you want to create your own tasks, the async feature is not for that. The task completion source is for that. Okay? And it's really rather versatile. You create one, hand out the tasks, and then you call one of the complete methods on it, the try set result methods on it, whenever something that you're in control of triggers that the thing is complete. Here's the when clicked method. It looks exactly the same. You can see, same deal, just even a tiny bit simpler. Somebody clicks, we now, or rather, you call it when clicked, so you wait for the click. You sign up an event for when it clicks to complete a task that you await, unsubscribe, return. Boom. You go out, completes, and you're done. Okay? Some people are taking photos. We should actually take a question from down here. I'll repeat your question for the recording. Await TCS.task. So the task completion source generates a task, right? And you can get, and this is how you get that task. You just ask it for it. It's in a property. So as soon as you created the task completion source, you can get the task. And then later, you can complete the task by calling one of the try set methods on the task completion source. It then tells the tasks that it handed out that it's complete. So there's sort of a one-way street between those two. Okay? Let's see what's next here. Well, to summarize, callback-based programming is always hard. Async takes away some of it, naturally, by handling all the cases where the callbacks were for async. But you can use it to deal with even more callback-based programming that's sort of more event-based, if you're just being a little smart about it. You use this pattern. It really cleans up your code, as you can see. And task completion source is your friend there. Now here comes a morality tale. Library methods should not lie. So what this one is about is not actually morals so much. Of course, it's good for your soul not to lie. But it's, at least they tell us. Maybe that's a lie. But the main point here is, I'll try to put it in more detail here. The main point here is that some methods are naturally synchronous. They do work. We're coming back to the CPU-bound versus IO-bound distinction again here. They do work. They utilize the CPU. They should be honest about doing work. And the way you're honest about doing work is that you're synchronous. You do something that occupies the CPU for a while, you should say so. If you're async, if you're naturally async, you're waiting for something IO. If you're not going to use the thread, you should be honest about that by being async. Okay? And we'll get into why this is important. So synchronous methods in the library signal, I'm going to perform work for you. You're not wasting your time waiting for me because I'm doing real work. Asynchronous methods means I'm going to initiate work for you, And here is where you can come back and check in and see if and when there's a result of that work and what the result is. Okay? So it's an important intention stated in whether your library is synchronous and asynchronous. It's largely about CPU bound versus IO bound. This is super important, and we'll see how. So here's a stupid little example. The thing we want to do is to pause for 10 seconds and then print something. So the completely synchronous doing work on the CPU way of doing that is to compute when we're supposed to be done, and then to spin a while loop until we reach that time, then print things out. It's kind of stupid, but it is honest work, right? It may be spinning a hamster wheel, but it's burning calories. It's burning CPU by doing so. Asynchronously, what we would do is, well, we could do it the hard way. We take that task completion source we just learned about. We could create a timer, ask it to come back in 10,000 milliseconds and complete that task completion source. But we can also just use the helper method called task.delay, which takes some milliseconds and returns you a task that will complete in that many milliseconds. It's kind of simple but super nifty, right? Give me a delay. Thank you. Give me a delay right away. I will wait for it later. So these are the honest versions. CPU bound, IO bound. It's not IO bound is sort of little. It's time bound in this sense here. True async there, and you want to say that it's async. You can do other stuff while this timer is set. Now, if you try to make an asynchronous method that really is synchronous, you're like, I want to offer this up as an async signature, but I have an asynchronous implementation of it. Then there's a way to fake it, and the way is to use task.run, another helper method which will take your work, put it on a thread pool, give you a task back for it, saying this task completes when that work is done. So we're really using the thread pool here. You're spinning threads in order to appear async. It looks async, but it isn't really, because someone is still doing work. So it's not IO bound, it's CPU bound. And that's pretty bad, and we'll get into why. This is even worse. This is taking async work and trying to make it look synchronous. So you call the asynchronous method here, and then you synchronously wait for the task. So you tell your thread, block until this task is done. This is a disastrous pattern. You should never do this. This arrow is really red because you should not do this. And let's get into details about why you shouldn't do these things. So should I give you async wrappers for synchronous methods? Generally, no. Should I expose synchronous wrappers for async work? Absolutely no. It's essentially the message. So if you look at the first one first, where you're using a thread to appear async, it's sort of like you're treating the thread pool, the work on the thread pool, the same way that you would treat a disk drive or the internet or something like that. You're saying, it's not my problem, it's doing work, but not right here. You're shoving the work off to the side. But the problem is, it's using resources that affect you. The thread pool is a global resource. The more you use it, the less there's left for others to use. Okay. If you do it down in a library, you're hiding from the app developer the ability to tweak and control and have just general awareness of where are threads being used, where are they being burned. Right. That's something that the one with the global perspective, the actual end user of the libraries, they have a much better vantage point for deciding when to use threads and how much. If you do that secretly in the libraries, they lose their ability to control that. Okay? If threads are a scarce resource, you just took it away from them. That's sort of the main reason. And in particular, if you're on a server, scalability is really hurt if threads are just being used willy-nilly. They run out maybe at a couple of thousand threads. That sounds like a lot, but it may not be, depending on what you're doing. if these things just look like little cheap async methods, you may be calling them millions of times. And you're just totally horking the system by secretly using a thread per each. Okay? Not good. The app is where you should decide whether to use the thread pool. The library is not. Unless the library is explicitly about threading, don't use threads in secret. Okay? Now let's look at the other way, the one where I have some async work and I just want to block it. I just want to make it look synchronous. It's actually much more dangerous than it sounds. Let's take an example from the UI thread. So I have a message pump on the UI thread, right? There's a queue of things to do, and the UI thread pulls things off the queue and does them, and then on to the next one. And while it's doing that, it's servicing the UI. So it's making sure that it listens to user input and is responsive and updating the screen and so on. So it has to have little pieces of work, constantly executing them, but in such a way that it quickly gets to a next point where it can be responsive. So let's say I have a button click running on the UI thread here that calls an async method, but yeah, I'm going to just wait for it. It's probably not going to take that long. I'm just going to wait for it synchronously. Maybe it's half a second. The user can deal with that in the UI, right? It's okay. It's unresponsive for a few hundred milliseconds. Who cares? It's much worse than that, though. Let's look at what happens. The user clicks. Button 1 click calls load async, which is an async method. And it calls download async, signs up a callback on the download somewhere, whatever task I get back from download async. And then it awaits, which means it returns to the UI thread. Oh, sorry, it returns to the calling method on the UI thread here. Then it calls wait, which means now the UI thread sits, leans back, and does nothing. Nothing. Now the download completes. The task that we are awaiting over in task load async completes. Well, that's good. But now we're trying to resume the method, the load async method, to run it to the end by posting the resumption back on the UI thread, putting it in the queue for the UI thread to run the next time it gets around to it. So there it sits in the queue, waiting to complete its task. But you never get to it in the queue because the UI thread is doing nothing. It's waiting for the task to complete. That is waiting for the UI thread to wake up so it can complete the task. So you have a deadlock, so it's actually never going to come back. And instead of seeing that short but maybe acceptable nuisance of unresponsiveness in your UI, you horked it. You deadlocked it. Okay? Because there is just the UI thread doing the UI work. And if you stop it, it cannot even complete the things it's waiting for. You see it? You probably had this many times. So this is why you shouldn't do this. If you're not running on the UI thread, if you're running on the thread pool, things aren't quite as dire, because on the thread pool is a little smarter about how it resumes asynchronous methods. They don't have to resume on the thread they started on. They can resume on another thread pool thread. And so as long as the thread pool is alive, as long as there's available threads to complete things, you don't gum up the works. But you can easily imagine blocking more and more and the thread pool kind of running out, and I'm just like throwing up its hands. I can't start more threads. I can't get any progress anywhere. Okay? So this is why it's so dangerous. So, library methods shouldn't lie. The thread pool is a global resource. It should be treated as such. Your global program should make decisions about how to consume that resource best. And it's a no-no to block your threads waiting for async work, because that async work may depend on that thread not being blocked. Those are essentially the things to keep in mind. So when you're looking at, should this method be async or not, think about, is it IO bound or not? And try to deal with that. You will find yourself occasionally in situations where it's really hard to be honest. Again, maybe you may be in a situation where you're overriding a virtual method that has one signature, and it's synchronous, but you kind of want, you need to implement it. You only have asynchronous methods at your disposal to implement that method. And so you've got to try to get creative. Maybe you suck it up and live with spinning up threads for that situation. Maybe you convince yourself that it's not going to happen that often or something like that. There are really situations that are hard to resolve or give general guidance around, but they're pretty rare. Most of the time, you can be honest, and your caller knows exactly what you're doing and not doing. They can trust that when you say you're async, you're not spinning threads. When you say you're sync, you're not blocking threads. Okay? Async, not spinning on threads. Sync, not blocking threads. Doing nothing. Cool? So those were the 4 big ones. We have some time left. So I want to get into a few more details that will also maybe help you use async to the best possible purpose. So here's one. Let's talk a little bit about what does it cost to be async? How expensive is async over sync? Okay? So the whole world has been doing synchronous for many, many years, and then we added this language feature that completely changes the paradigm for execution. The CLR knows nothing about async. Our optimization strategies in the CLR know nothing about async. We as compiler people are just figuring out how to deal with async. And async is inherently more complicated to begin with. So there's bound to be some extra cost. Let's kind of look at what they are and when you should worry about them. So synchronous methods are cheap, right? You have a synchronous method here writing out a string. Well, this is what the IL looks like. Okay, it's a couple of lines of IL. Even if you don't read IL, you can see, okay, this is not bad. This is the kind of thing the CLR was built for. No problem. If we couldn't print out a string synchronously, we would have a really bad VM there. So, so that's kind of obvious. Now, what is the corresponding asynchronous situation here? You have an async method. It doesn't actually await anywhere. You'd actually get a warning in the compiler if you compile this. But just by the fact of having it be async and task returning, what code gets generated now? I'm not going to go through it in detail because it's quite a lot. So this is what gets generated for that method. This is the body of that method. So it's kind of 3 times as long or something like that. So that looks pretty hairy. But it turns out that this is just the method to initialize the state machine that the asynchronous method is going to be running. The actual code that's going to be running in the state machine that the compiler generates every time the async method gets resumed after an await is getting called here. It's the move next method. It's a helper method the compiler generates for this. And it looks like this. Whoa. And I should not laugh. There'll be ER personnel outside after the talk to help you with your ears. So, but it should be painful, right? Because look at this. This is the code for the state machine that gets generated in order to service a method that doesn't even await anything. If you squint a lot and look careful, and I put a green box to help you, you can see that the source code of the original method, this is where it goes. All the rest is mechanism. So that's a lot of code corresponding, if you compare it to what we did in the synchronous case. That's not necessarily a problem. It's not necessarily a big problem. It's a lot of code, but it can still run pretty fast. The thing to primarily be concerned about is how many allocations are involved in doing the whole async thing. I mean, there's got to be some allocation. I'm talking about a state machine getting generated by the compiler. Normally when a method runs, it has local variables on the stack, and stack is cheap to allocate on. But if you need the method to be able to suspend and come back later, then you need to save all that local state somewhere in an object. So there's an object that needs to get allocated for a state machine to hold on to local state until we resume, while it's not being executed and while it doesn't live on the stack. So there's an allocation there. It returns a task. That task needs to get allocated. So all of a sudden there are object allocations involved here. Actually, object allocation on the heap is also cheap. It's cleaning up after it that's expensive. If you had an infinite heap, it wouldn't be a problem allocating there. But in practice, we don't. So we do garbage collection. And the more garbage we produce, the more we have to collect, and the more it starts impacting performance. So it's worth assessing how much allocation goes on when you do an async method. So here are the 3 things that need to be allocated in general for an async method. The state machine holding the variables, a delegate to sign up on the things you're awaiting, and a task object to return. Okay? Those are the 3 things that you cannot generally avoid allocating. Now, we try to optimize this a lot. So if you actually have a situation where you don't run into any awaits, maybe there aren't any in the method, but that's pretty rare because it's pretty dumb. Why would it be async in the first place? But you could also just be taking a path through the code that happens to not hit any awaits. That could be very common. Think about a buffering scenario, right? Every millionth time, I need to go and download the next chunk from the internet. So there's really some asynchronous awaiting here. But the rest of the time, it's in a buffer and the stuff is already there. And I may be taking a code path where reading it doesn't actually cause any delay. And so for those situations where there's no delay, where there's nothing to await because it's already done, we can skip those 2 allocations. We only do those the first time we hit an await that actually needs to await in a given method. So that's good, 2 out of 3. Here's an example of that where we await get next int here, and if what the compiler generates is essentially a check to see if the thing we're awaiting, we get something called an awaiter. It's kind of an implementation object, a struct. If that thing is completed, then don't do anything here. Just grab the result and go. Otherwise, do all the state machine, sign up, blah, 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 blah. So we call that the fast path. And the compiler does this as sort of an optimization. It's a very important optimization. OK, this last object here, you can also actually be lucky that it doesn't get allocated. We have a few very common values. Like if your method doesn't have any awaits that actually fire, and you happen to return 0 or null, or one of those very common objects. We already have a task lying around in a global storage somewhere that represents a completed task with the result of null or a result of 0. We have a few of those cached for you. And so the machinery around async is smart enough to grab one of those and return it. So you might actually see, if you compare tasks by identity that are returned from async methods, you may sometimes see the same task come back more than once, because it happened to be the task for already completed 0, and you get that a lot, so it's the same task. When you await a task that's already complete, that's no problem. You just get the result immediately. So that all works out fine. So you can sometimes avoid those. You can just be lucky by the structure of your code that you avoid those allocations. And also, even if you have your own common tasks, you can sort of do a little extra work to cache common values yourself. So you can have a kind of a wrapper for your async method maybe where you don't generate the task but reuse one if you know the result is going to be the same. Now, is all this allocation actually a problem or not? We all sort of, not all, but all us on the compiler team, we're sort of neat freaks in the sense that we don't, if anything costs anything, we don't want to do it. We're misers with performance. But the real rule of thumb about performance is don't worry about it till it hurts, right? Keep your code nice and clean. Use async to your heart's content. And it's never going to be a problem for most of you ever. And for a few of you, it may be a problem a few times. If you're doing async stuff in an inner loop, then all this, if you're doing millions of async calls in an inner loop, then maybe it starts to add up. Maybe it adds up to a delay or something that isn't optimal. Then you can go do something about it. But other than that, even all that extra code and all that stuff, it's not really a problem in most cases. Remember, we're dealing with async. And async is about dealing with delays that are orders of magnitude larger than the kinds of delays that a little lack of performance gives you. Right? I am waiting for hundreds of milliseconds for stuff to come over the wire. What does it matter that the machinery, the bookkeeping around getting all that stuff, kind of put together and executed in the right order? What does it matter that it is 3 or 4 times as expensive as, corresponding synchronous code would have been? Because that corresponding synchronous code would then have also blocked a thread for those hundreds of milliseconds. And that vastly, completely dwarfs the cost of async. So most cases, the more async, the better. It's going to do great for your perceived performance, for the feeling of things being responsive and all that kind of stuff. But there is a risk in inner loops that all this extra allocation and extra code and so on will be a cost. So just be aware of it. Just know what's going on under the hood. And now you know because I told you. All right? So that was the next to last thing. I want to, staying on this performance thing, I want to just touch on one last thing. If you're building libraries, here's the problem. It's easy to do performance testing of an app, right? Because you know exactly how it's going to be used. You put a user interface on it, that's how it's going to be used. You go through all the different usage patterns, automate or whatever, and you know the performance of all the scenarios in the world. But if you're building a library, it's a much more open-ended world. How people are going to use your library, how frequently are they going to call you, how much are they going to benefit from the optimizations I just talked about. On the other hand, when you're building a library, one of the things you don't know and probably don't care is which thread you're getting called on. Like, you don't know that I'm always going to get called on the UI thread. I'm always going to get called in some other context. One of the things that is also expensive about async is that it keeps track of, when you await something, it keeps track of where were you originally called, and it tries to get you back to the same place. There's a notion of synchronization context that's sitting in your thread somewhere, and every thread has the option of keeping track of a synchronization context, which is essentially a where do I live kind of object. Okay? On the UI thread, it has a synchronization context saying, I live on the UI thread. And what await does when it resumes execution after having been off for a while, when the awaited thing completes and the method resumes, it has to make a decision about where should I run this next chunk of code. And what it does is it walks up to the synchronization context that was in effect before the await and says, let me run it there. The thing you can do with the synchronization context is you can walk up to it and say, here's a delegate, here's some work. Do that, please. Do that at home, so to speak. So the UI thread has a synchronization context that will run work on the UI thread. The thread pool has a synchronization context that will run work on the thread pool. ASP.NET has a synchronization context that will run things on ASP.NET. Okay? So there's this extra mechanism making sure that after an await, it looks like you are where you were before. Nothing changed. I was in a UI thread, I'm still in a UI thread. It'd be super confusing if you were running an event handler, you await something, and all of a sudden you're in the thread pool. All of a sudden you can't call UI methods anymore because you can only do that from the UI thread. Like that, what kind of experience would that be? But that extra level of bookkeeping, that putting you back where you were, is also a bit expensive, right? It's work. And in library code, you often don't care where you're running. Most library code has no desire to run in a particular place because it's generalized over that. And so what you can do is you can ask, when you await something, you can ask for the continuation of that, the rest of the method, not to be put back, but just to keep going wherever the thing that resumes you was running. So you can save a step of posting back. And that's just good practice to do when you're writing library methods because your library will get faster and it's not going to hurt your user. They're still going to get the caller is still going to get put back when they're done awaiting you. So I just said all this stuff. So essentially, use the trick that is shown here in very small letters called configure await. When you have a task, you can call the method called configure await on it, and if you pass false as an argument, it's very obvious, but the parameter name makes it more obvious, then you're essentially asking not to be put back where you were before the await. You're turning the task into another kind of task that doesn't resume on the place it was before. And that way, say that you're doing await x plus await y, who cares where the plus is executed? It's a plus. And so you do await x dot configure await false and y dot configure await false added together, and those things won't cost you nearly as much. So it's good practice for library code to do this, especially if you're in places where very little work is done and it's stupid to post it to a particular thread. Just do it wherever you happen to be. Okay. So that is the last bit of advice I have for you today. We have 4 minutes left. I want to quickly point to all the related talks are in the past, but they're recorded. As I said, even if the task is completed, you can still await it. So that means you can go to the. Thank you. So even though those talks have run to completion, you can still go and observe the result of them with an await. And I have to confess that I have to run off right after this talk because I'm on channel 9 right after. So I won't be around for questions sort of individually at the stage. But I will go to the booths, the Visual Studio part of the booths, the languages table, and hang out there when I'm done with that, probably around 1:30 until they close at 3. So if you have individual questions, come and ask me there. We also have 3 minutes now in the room. And so if you have questions that you want to ask in a plenary setting, we have microphones. We have lots of people running for the doors. They want to get to the restrooms before everyone else. I should have pretended not to be done yet. You would have done it anyway, wouldn't you? So any questions, please come up to the microphones. Or if you can't because of the traffic, please raise your hand really high and shout out your question really loud.
The library naming, you shouldn't lie when you name methods in your library.
Yep.
It seems like something the integrated development environment should tell you about. It should hint you about it when you do wrong, such as when you use resharper. Does it do that?
So that's a great question. Sometimes it's a little hard to know. It's just from a static code analysis point of view. It can be hard to figure out whether a piece of work is actually I/O bound or CPU bound, and for it to therefore give you the right advice. In particular, if some of the code is running in a different assembly and you can't actually inspect the code. But it is a great idea, and I think that tool support honestly can get a lot better with that. I will plug the next version of Visual Studio, which has what we call Roslyn. That was in my other talk, the related talk up there from the future of C# and VB, which in the future will make it a lot easier for people to build their own analysis as well. So I expect we'll see a lot of these suggestions I've given here showing up as actually actionable diagnostics and fixes in future UI experiences in VS, either from us or from other people using the Roslyn framework to do so.
Could you give some very common examples of great usages when it would be useful to use asynchronous calls?
Of what, sorry? Of situations where you want to use it?
Common scenarios where you would like to use asynchronous calls.
In the scenario that I showed a lot here is doing apps, store apps. You actually, if you look at the Windows runtime libraries, for instance, most of the important methods there they only exist in an asynchronous version. You cannot even avoid doing some form of asynchronous programming. And the only way that isn't excruciatingly painful is to use the language feature to call those methods and await the result. It is really the Windows runtime library is trying very hard to make you not block anything, to not give the users of your app a bad experience. And so they do that by just not giving you the synchronous version of a given API. Is this a line for questions?
Yeah.
I will skip to the QR code for feedback in case somebody wants to grab that. And then I'll take, we're probably running out of time for the recording, but I'll take a few more questions here.
Yeah, the internet seems to be pretty divided on this one, so I wanted a more definitive answer. ASP.NET, page load, async or not?
I can't hear what you're saying. Is the microphone? Oh, the microphone is off. Okay.
I'll come
Apparently, we can't take questions here. So come find me at the booth at 1:30, and we'll do them individually.
This one works.
That one works. I'm sorry. The timer also says we're done. So thank you very much. And then it returns. So the method returns back out for resumption later. Well, the next thing I'm doing up here in my event handler is I'm also awaiting something. So now I also return to my caller, whichever thing fired the event in the first place, and I'm out. Sometime later, so now I'm awaiting in two different places. Sometime later, one of these will resume, and then sometime later again, the other one will resume. But we don't know which order they'll do it in. Maybe most of the time, the send data, the await and send data will fire first because typically it won't take 2 seconds to request something, but maybe one day it does because the network is slow, and you see these strange, apparently non-deterministic failures happen where it didn't get everything before it needed to. So that's one way that you see it. Let's look at another variant here where we're not even waiting for the result to come back. Another issue that happens here, we come in, so same as before, we get into send data, we await the request. Now something else happens. The thing that we're trying to, the get response async method that we're trying to call here, it actually completes with an exception. Something went wrong, okay? So when something goes wrong in an async method, then the task that the async method returns still completes. But when you await it, you get the exception out instead of a result. So what happens here is that the await throws an exception. But the exception happens after the method has returned. So we await, we return to our send data method, return out, and then watch in a few more, but we may not have time. So first of all, async on void returning methods is really dangerous. You might ask, why did you put it in? Well, it's also really necessary. But it's one of those things that we want to warn you of as a common smell, and we're going to look at some of the examples of why it's a bad idea, how to work around it when you have situations involving it. So that's one thing. The other one, the next point we want to make is about essentially the difference between CPU-bound code that's heavy work and wanting to run that in parallel versus IO-bound code that is essentially work that takes a long time but is not happening on your machine but somewhere else out there, like downloads and stuff like that, and how that should impact your code. We'll look a little about how you can use async to clean up messes around event-based programming that can get very hairy sometimes. So there's some tips and tricks there. And finally, an important thing that we'll look at is when you write libraries, you should make sure that they don't essentially lie about what they're about. If they're not really async, don't make them look async. If they're not really synchronous, don't try to make them look synchronous, if you can avoid it. So let's start right out. We had a user. I'm gonna actually read from an email that we got from a user around this kind of problem. I have a Silverlight page that uses RIA services async to download the data for the page, and this works fine if the user waits for a few seconds before they click on the print button. But if they click the print button right away before the data is loaded, then somehow the print doesn't have all the data. What's going on? Maybe you recognize this kind of thing. Okay, apparently something wasn't ready when I clicked. Once the task is complete, the event throws an exception. However, the exception doesn't come back to our original caller, and it doesn't get caught by the catch handler because we're already out, right? No one was there to hear when things went wrong and to deal with it. What happens instead when you have an async void method that throws an exception, because it has no task to put the exception in and say pass it on or whatever. What happens instead is it looks at where it's running and it takes that thing down. All right? So this send data method here, it's running on the UI thread. It goes to the UI thread and says, I have an exception. I don't know who called me. He's gone long ago. I don't know what to do with this exception. The UI thread says, fine, let me kill the program. You got a crash. Okay? Even though you have a nice try catch up in your event handler there, you are not awaiting the exception, so you're not catching it. Okay, so these are two flavors of this thing going wrong. So the principles that are worth keeping in mind here is that async void is really a fire and forget mechanism. That's what you saw. You kick it off, and there's no way that you can know what happens next. Because you're only getting void back. You're getting nothing back to talk to say, what happened? Did it go all right? What was your result? It's fire and forget. And fire and forget is almost never what you want. You can't know if it finished. You can't know if it threw exceptions. So what you should do is only use async void when you absolutely have to, when you're top level. And that's typically in an event handler. It can also be things that aren't really event handlers, but are used the same way. So async void virtual methods, we'll see an example of that shortly. It's a way that people have event-like stuff. You really, really, really have to return tasks whenever you can. Whenever. All right, I think that's my cue. Welcome. Have a seat if you don't already. I'm Mads Torgersen from Microsoft. I'm the program manager for the C# programming language. I'm the guy who gets to enjoy writing the language specification and run the language design process. So I was one of the people involved in putting the async feature into C# and VB in the first place. Oh, thank you. Wow. Okay, we're done. Bye. So I guess we have some fans of that feature in the audience. That's good. So let me start out by a show of hands, even though I can't actually see much from up here. How many people have used the async feature in some way, shape, or form? Okay, that's good. That's the majority of the audience. How many have not? A few. Okay. Okay, we probably don't need much of a primer. I apologize a little if you haven't looked at it. And how many are other? Oh, okay. Everybody has either used it or not used it. That's good. So this talk is going to focus on various, it's called async best practices. It's going to focus on various problems or situations that we kind of realized after we put the feature in and started having people use it, that, okay, there's some things here that are really hard or that people struggle with. And we tried to take some of the most common ones and boil out the best guidance for dealing with those. And that's what this talk is primarily about. So the 4 points that I want to make sure that we get through in this talk are here. I'm going to say them up front. You're going to probably forget all about them, but we'll visit these along the way. And if we have time, we can talk. So this kind of code here. And when we looked at the code, it turned out that they were using async void in places where they shouldn't. I'm not actually going to share the code from this user because it's a little involved, but we're going to, let's make the point really clear here. You should not use async void unless you absolutely cannot avoid it. Anyway, so I'm going to use a different example here that that's simpler but highlights the issue of using async void. So it's very common looking code here. I have an event, a button click event. It's calling an async void method. The event itself is async void. It's calling an async void method to try to send some data. And it gets a response back, and it assigns it into a variable. And then after the button click has called the send data method, it waits for a little while. Then to make sure, hopefully the data got, the thing got through. We kind of put a delay in to make sure that the interaction happened. And then hopefully the variable filled up, and we can print things out. Now, of course, if you look at how this executes, when the event handler is called, control comes in, we call send data. It goes to the send data method, starts executing it. Now, as soon as it comes to the first await, you guys know what happens? Yes, you do, but you're not going to tell me because he's doing the talking. I'm sure they pay him money to do talks. Why should I? You know. So what happens when you reach an await is that your method returns. You know, what it does is it signs up a callback on the thing you're awaiting to say, resume me later,